Hi everyone, welcome to Intelligent Healthcare and its Applications course. So in this lecture, I will show you how to use multiple linear regression that we have learned in the previous classes to make a prediction of the brain age using MRI data. Okay, so let's move on to our today's lecture. Okay, before the time that we invented the magnetic resonance imaging or any imaging tool that can look into the brain, that people really don't know what inside the brain and how brain works. So that is really a mystery. So it has been a long time that the people think about how brain works and what's inside the brain. And it has been developed a theory called phrenology. So this is a typical phrenology representation of the brain. So you can see that at that time, the scientists, philosophers, they all think about what inside the brain. So they picture that maybe the memory is in the front of the brain areas, and there are other areas, maybe there's area control and interpret the time, and also there's an area control for the friendship or the other functions. Okay, so these are really not what we know today, but in the older time, when the people have no tools to study brain functions, they use any kind of imagination and some deduction, and they invented this kind of phrenological representation of the brain. So after the magnetic resonance imaging has been invented, now we have a very sophisticated tool that can look into the brain, and not only just look into the brain, we can actually take a picture and even measure the function of the brain. So that is really a huge advance. And so using the MRI that we have developed many useful protocols and analysis to understand brain functions. So today's lecture is that I just want to show you what is MRI, and so for those students that is not familiar with MRI and not familiar with the neuroimaging studies, so these lectures will give you an overview and insights into how brain MRI can help to understand brain functions and even its the pathological conditions. Okay, so what is magnetic resonance imaging? So an MRI is really a very useful technique to look into our body. So in an MRI machine, there is a large magnet, and this magnet is so strong that it can just, you need to be very careful. You cannot bring anything metal inside the MRI room, because this strong magnet will just attract all metals onto its body, and it's very dangerous. And there are accidents happened every year that the people just being very careless and bring metals into the room and cause the accident. And also because it's a very strong magnet, so for those have done surgeries using, for example, they may have the bone fractures, and they attach a metal to fix the bone. And for these patients, they cannot be inside the MRI room. And also for those with the pacemakers, and they cannot also undergo magnetic resonance imaging study because these strong magnet will just affect the functions of these, like pacemakers or any other metal things. But why we need this magnet? That is a very important question. Because with this magnet, then we can just turn every particles in our body to a single direction. So every atoms, every particles, they have their own the direction of the spin. They just, when there's no magnet, they just point to everywhere. But when there's a magnet just surrounding our body, then this magnet will cause a strong magnetic field that can align every atoms or particles into the same directions. So that's what we call the B0. And now, then we can let MRI machine to create another radio frequency pulse. And this radio frequency pulse is another, we can change its magnetic fields. So it can alter the direction of the atoms or particles. And you can imagine that because every atoms or particles, they have different weights and different magnetic characteristics. So each different atoms or particles will have a different behaviors under a radio frequency pulse. And when this radio frequency pulse is released, then it will, the particle or atoms will return to the original directions, which is defined by the B0, which is the big magnet here. And this release of radio frequency will result in the energy release from this action. So you can immediately picture that the different atoms and different particles, they will release different radio frequency energy. And we can use the magnetic field detectors to capture these different types of radio frequency energy and use mathematics to calculate then what is this particle and what is this particle. Then we can reconstruct the images from these energy patterns. And so that is the whole point of the magnetic resonance imaging. And that is really very creative because the inventors of the MRI, they got the Nobel Prize. And with this invention, then we now be able to look into the bodies without radiation. So I need to emphasize that the radio frequency is not equivalent to the radiation. Actually, it's just the radio waves that we commonly experience every day. So we experience the Wi-Fi signals, we have the cell phone signals, and even the visible light, they are all radio frequency waves. So these waves are energy that we can capture and try and use this MRI resonance imaging. We can capture differentiate the different types of molecules or particles, or like waters or the fat, and inside our body. So that is very useful because we can imaging body without radiation, just like a chest X-ray, or because in the X-ray, although we can take a picture of our body, but ultimately it is a radiation. But MRI machine does not have radiation. That is a very important difference between the MRI machine and the X-ray type of machine, for example, the computed tomograph. So So this is just a basic principles of the magnetic resonance imaging, and just let you know that this machine can really take a very high resolution of the picture of our brain. So this is the results of the MRI brain imaging. And with the appropriate protocols that we can produce the contrast between the gray matter, white matter, and cerebral spinal fluids. So what is the gray matter? So in these MRI images, you can just intuitively see there's a thin layers of the gray tissues surrounding our brain. And inside these gray tissues, there's a white tissues just spread in a large part of our brain. And inside the brain, there's a black regions. There's a black regions here and black regions surrounding the brain. These are actually the water fluids. So we call this cerebral spinal fluids because these fluids can connect to the cerebral ventricles and spinal cord. So that is a very important protective mechanism because we need these CSF fluids to protect our brain. So it's just like a cushion. It can prevent you from any impact and maybe just minor impact, but it's already very important because you don't want your brain touch your skull, and that would be results in a very terrible situation. So intuitively, there's a gray tissues here and a white tissues here, and then we just call it the gray matters and white matter. And gray matter is actually the location of the neurons. And the white matters is just like the wires of the neurons, it's neural axons. So you can imagine that there are lots of axons projected from the neurons out in these thin layers of the brain and project into a larger part of the brain areas and they connect to each other. So it just for the white part, it just lots of neuron fibers, axons. They connect to each neuron. So it's a very complex network. And so that's why the brain is so complex that it's still the final frontier of our medicine, okay? So, but don't be so excited because even with the MRI image, then we can achieve the resolution as high as 1 millimeters. So that resolution is really dependent on the level of magnetic fields. For example, typically in the hospital, we will have the MRI machine with 1.5 Tesla or the 3.0 Tesla as the level of the magnetic fields. The Tesla is a unit to measure the strength of the magnetic fields. And the larger the Tesla means the larger magnetic fields. But usually in the hospital, we use the 1.5 or 3 Tesla. And if you increase the magnetic strength to like 7 Tesla or even higher, then it is possible that you can achieve the higher resolution of the brain tissues or even the other parts of the tissue. But that also put into some risk of the higher energy of the radio frequency influence. So that is now this strong MRI machine is still undergoing clinical trials, but regularly that in the hospital we have only 1.5 and 3 Tesla, and the resolution we can achieve with this machine is about 1 millimeter. So just keep in mind, even for this 1 millimeter, there are lots of neurons, but so the resolution with the MRI machine is not so low, but also not so high. And there are still some improvements we can make in the future. And to obtain this kind of images, you need to lie in the machine for about 5 to 10 minutes. And with other protocols, you might need stay in the machine for a longer time, but that's just the time you need to obtain this kind of high resolution brain results. Okay. So with this structural MRI, then we can do something. So this MRI is very important in the clinical care, because when the people or patients have some neurological symptoms, then in the past, when the time without MRI, then you need to do some neurological tests. You might want to, for example, you might want to test the muscle powers of the bodies. And if you have a weakness in the right hand or left hand, you might just can try to locate the origins of the pathology in the brain. But this is not very accurate, although this is very useful and very important physical examination techniques. Every doctor needs to learn this technique to examine patients. But with the MRI, you can directly look into the brain and see what happens. So the structural MRI is really very important in the clinical care. And however, the most psychiatric and neurological disorders are invisible to the radiologist. So what I mean is that, for example, in this image, you can immediately see the asymmetry between the left and the right hemispheres. And you can immediately diagnose something with these MRI images. But for many psychiatric disorders like schizophrenia, bipolar disorders, even major depression, or neurological disorders like Alzheimer's disease, Parkinson's disease, they do not have the visible patterns. So because these diseases do not have visible patterns, then radiologists, which is the pattern doctors, they cannot recognize this disease just based on the MRI imaging. So, for example, what disease can be detected with the visual readings of MRI? For example, the brain tumor, then you can find this very high contrast of the tumor comparing to the other part of the brain. And also you can scan the stroke. And when the stroke happens, it has the ischemic change in the brain tissues, means that it doesn't have the sufficient blood, or the blood has been blocked from transporting into this brain tissue. Then you have some protocols to highlight these regions. And also, for example, you may have the cranial hemorrhage. So this is a typical epidural hemorrhage that happened between the brain, outside the brain, and around the dura matters. So using MRI, then you can diagnose the brain hemorrhage. So you can see that this brain hematoma, which is accumulation of the blood, it can just compress the brain tissue, and it will result in some neurological symptoms. So that's a huge advance, because in the past time without MRI, then we can only guess what happened inside the brain. But with the MRI, then we can do the diagnosis and give the necessary treatment. So that is the useful part of the MRI. But however, just like I said, we think if in many neuropsychiatric disorders, there's no visible patterns. And even just look at the brain MRI, then we might have only just a guess that what happened with this brain. For example, we have two brain scans from two people. One is the young people, and the other is the older people. And I just want to ask you, which one is the older brain? So let's take 10 seconds to make a guess, or just make an educational guess. Okay, so I think you might have an answer. And if you pick the right, this person is older person, then you are right. So this brain is from older people who's at 80 years old. And this brain is from younger people at 30 years old. So what's the difference between these brains? So you can see there's the brain is very intact, and there's no much black space between the skulls and the brain tissues. That means the brain has no atrophy, which means that the decreased volume of the brain. And in the aging, that the people typically will have loss of neurons, and this loss of neurons will result in the decreased brain volumes. So in older people, you typically see the brain atrophy. So the brain atrophy will also result in the increased the cerebrospinal fluid volumes, just like this ventricle volumes and the surrounding CSF volumes is also increased. So that is the hallmarks of the aging. So that's why in these lectures, I want to show you how to use MRI imaging to predict the brain age. And you'll probably be very excited that we can use this raw data to predict brain imaging, but just not so fast, because remember that we only learn about the multiple linear regression in this course. So I will give you some data about the brain volumes, and you will use this brain volumes to predict the brain age. Okay, so let's take another guess. So again, we have two brain scans, MRI scans. Then which one is the demented patients? So dementia is a neurodegenerative disease that it has a declined cognitive functions. And put it very straightforward, it just has a declined memory and ability to do everything task in the daily life. So these two brain scans are from two older people. They have the same age, just like 70 years old. So can you guess that, or make an educational guess that which one is the demented patients? So let's take like maybe 5 seconds. Okay, so I think that some of you may be thinking the left one has dementia, and the right one, some of you think that the right one has dementia. And the answer is that the right one is the demented patients, and the left one is the older person with the same age, but he does not have the dementia. So he's he has a healthy cognitive functions. So what's the difference? So you can see that in the older age, they all have the brain atrophies, but not everyone with brain atrophy has the dementia. So what's the hallmark about dementia? And typically, we will look into the temporal cortex, because the temporal cortex is the region that very close to, like, for example, the region like hippocampus or the other region is very close to these subcortical regions. And the temporal cortex is usually the first brain regions that shows the brain atrophy in the dementia. So you can look at these regions, you will find it has a profound brain atrophy in the temporal region compared to the healthy older people. So that is the one possible findings that you can see in a demented patient. But I need to emphasize that this is not still sufficient to make a diagnosis by radiologist, because even these patterns cannot be very consistent through every demented patients, so we cannot use these patterns to diagnose dementia. So that's why even in a neurological disease like Alzheimer's disease, it's not very easy for doctors to look at the MRI to make a diagnosis. And even more difficult is that for the psychiatric disorders. So for these two brain scans, they are from two younger people, like at 30 years old. And just try to make an educational guess that which brain has the mental units. Just maybe take 5 seconds also. Okay, so I know some of you might think the right one is that maybe just has the mental units, and the left one is normal people, but actually the left one is a scan from the patient with schizophrenia, which is a very severe mental illness characterized by the hallucination, delusion, and the declined cognitive functions. So you can see that there's no significant brain atrophy in these schizophrenia patients. Actually, in the right one, you think that there may be brain atrophy, but that is not that is only a normal variation of the healthy people. So in some people, healthy persons, then you can see they also have a larger brain vesicles, and there's some increased volume of spinal fluid in the frontal area. So that is the normal variations. So again, I want to emphasize that there's really no consistent visible patterns in the neuropsychiatric disorders in the brain imaging data. Okay, but then why we still want to do this today's course? Because even the human eyes cannot find the visible or identifiable patterns in the brain MRI imagings regarding the neuropsychiatric disorders, but we can still use the mathematical analysis and very detailed comparisons of the brain imaging and to find something difference between the healthy and the patient with the pathological conditions. And even in the brain in the aging studies, then we can also use these very sophisticated imaging tools, imaging analysis, to figure out which brain region is really very important in the aging. So one of the basic analysis in the brain imaging is the brain segmentation. So with these structural imagings, then we will find that there's a very interesting distribution of the brain intensity of brain voxels. So the voxel means a small cubic that we just in the brain. And for the imaging data, then we can look into every voxels and to identify the intensities. And we can find that different tissues have different intensities. For example, the gray matters and white matters have different intensities. White matter have a higher intensities, and gray matter is in the middle, and the CSF region, it has the lowest intensities. If you just put intensities of every voxels onto a histogram, which is just accumulated count of every voxel's intensity, then you will find that there is not a normal distributions. is a mixture of the different Gaussian distributions. So we can use some mathematical analysis to reconstruct these different Gaussian distributions. So for this one is the white matters, and for this distribution is for gray matters, and for this one is for the CSF regions. And when you sum up these three distributions, you will have this red line. So we can just to use mathematics to deduct these three different distributions and to give a probability that if this one has a probability for the gray matter or white matters. So for this one, it could have the moderate probability as the white matters, but maybe have the low probability for the gray matters, but have the zero probability for the cerebrospinal fluid. And for this one, maybe have the very high probability for the CSF, but have the nearest zero probability for either gray matter or white matter. So that is how we analyze the brain, because we use these image intensities to classify the voxels into three different types of the brain tissues. So one is the gray matter, and the other is the white matter, and also we have the CSF regions, which is the waters. Okay, so this is summary of the brain segmentations with the structural brain images. Then we can standardize the brain imaging with the a standard template. So that means that we can project everyone's brain to a standard brain areas, so that we can compare one's brain to the other, because everyone's brain, the shape is different. So we need to convert this shape to the standard shape. And then we can do the segmentation to divide the brain into the gray matter, white matter, and the CSF areas. Then we can also do some normalizations. Then we can derive the standardized, the normalized probability for each voxels. Okay, so for this analysis, then we can do a very detailed comparisons for the intensities in each voxels, or probabilities in each voxels for gray matter or white matters. Then, for many studies, they found that the patients, for example, the schizophrenia, they actually have the brain and the reduction in the gray matter valence after the onset of the units. So this is comparison between the onset of units and the patient in the 5 years later. So it means that the patient really have the brain valence reductions under the influence of the disease, although these brain valence reductions is not really visible to the human eyes, but they can be quantified by the brain imaging analysis. So this is a very robust change in the brain valence in schizophrenia, or even in the bipolar disorders. So that is why we can use the brain MRI to do the diagnosis or do the prediction of the brain age, just like what I showed in this lecture. So likewise, in the Alzheimer's disease, there is also a change in the cortical thickness. And this change in the cortical thickness means the loss in the gray matters. So the comparison between the patient at at the time of the diagnosis and the 12 months later, it shows there is a brain atrophy in a certain brain regions. So again, this is not visible to the human eyes, and we can only visualize this with some analysis, and we can color this difference so you can see the brain atrophy. So that is something we can do based on the data science or analytical tools. So of course, the brain volume declines with age. So this is one study show you that there's a group of the non-demented the subjects, and also there's a patient with dementia, and usually the dementia happens in the later life. So you can see that these demented patients have age above around 65 years old. And most non-demented participants, they have an age around 15 to like 95 years old. So it doesn't necessarily that the older age have the dementia. So you can see that they're in the older age, they have people with dementia and without dementia. But you can see it seems that the brain volume declines with age in a nonlinear fashions. And for those with dementia, you can see they have even greater decline of the brain volume. That is the one hypothesis that the Alzheimer's disease can accelerate the brain volume reductions. So that is the one results that we can found in the brain studies. So today's course that I want to show you, if we have the brain volume data, then can we use that brain volume data to do a regression line? Then we can predict the brain age just based on the brain volumes. So that is the question we want to answer in this course. So the data we used will be from the gray matter area. So for these data, then we can derive the brain volumes from a certain brain regions. And the way we achieve this is to divide the brain into several, not several, just in the numerous small voxels. And each voxel is just a small cube. And as I said, for the resolution of the structural images, we typically can achieve like 1 millimeter cubic shape. So you can see that we can just divide the brain into millions of the brain small voxels. Then for each images, then we can divide the brain into different areas. And we can sum up the brain volumes. We can sum up the gray matter volumes in these areas and to get some quantitative results. So we will use these volumetric measures to do today's work. Okay, so the data we will practice today is from the Taiwan Aging and Mental Illness cohort. And this is the cohort that I and Dr. Tsai at the Taipei Veterans General Hospital have collected and studied in the past 8 years. So we already enrolled hundreds and more than 1,000 of the participants. And because of the IRB regulations, I cannot give you the identified data. So I cannot even give you a raw data. So even for the age, I cannot give you the correct age. So just keep in mind, the data I gave you does not corresponding to the correct actual age for that participant. I already do some age adjustment in this data. So you will not be able to identify a particular person for this using any of these metrics. But actually, these are still the true brain volumes as from these subjects. So we have some important brain regions like precentral areas, post-central areas, precuneus, anterior cingulate, posterior cingulate cortex, and also the famous one is hippocampus and parahippocampus. They are related to the memory functions. And also we have the insula amygdala, thalamus, caudate, and of course we have the total gray matter volumes. So this total gray matter volumes is usually the metrics that we measure the brain size. And you can see that the brain size is typically from like 500 cubic centimeters to maybe like more than 700 cubic centimeters. And in the older time, the scientists think that the size of the brain is related to the intellectual ability, but that is not correct. That we have knew that today. And also, for the case presentation 1, you already found that there's a difference of the brain size between the male and female, but that doesn't relate it to the intelligence. So that is the brain volumes here. Then for this, the identified data, and I already made it very de-identified because the age is not really a true age, but still there's a correlation between the age and the brain volume data. So that is a very nice example you can practice on the real medical data, and then you can use these brain volumes to predict age. So that is one applications we want to illustrate in this course. Okay, so for that data, you can download it from my laboratory website, and it is called the brain age prediction.mat. So for these files, you can use the simple function, use load brain age prediction data, then you will find a variable data in the workspace. Okay, so the first things that before we jump into the machine learning, I think it's a very good habit just to look at the data. So the first thing we will do is to visualize the relationship between age and total gray matter volume. So then this is a very simple task, because when you load the brain age prediction data, and for that the actions, you will have a data tables in the workspace. Then you will just plot the data.age against the data.total gray matter volume, and with the O shape the dot, then you will have this result. So we can also further label the horizontal axis to be the age in the unit of year, and also the vertical axis as the total gray matter volume in the unit of cubic centimeters. So for these results, you can see that for these 100 participants, they really have a decline of the gray matter volume over in accordance with the age. So we have the participant from the age 20 to around the 80s, and you can see there seems to be a line that you can put here to describe the linear relationship between the age and total gray matter volume. You might also think that this is not a straight line. It may be a little bit curved. So that is a challenging task, that what model that we can apply to this kind of phenomenon, and can that model explain the mechanism of the brain aging. But for now, we will just focus on the machine learning. So we will use the knowledge of the machine learning that we have learned in the past 2 courses. Then you will apply that knowledge to fit the regression line here, then to evaluate the model. So I think that most of the students, or maybe everyone, already be familiar with the simple linear regression. So we will not repeat that part. We will jump to the multiple linear regression. So our task is that can we use the 12 brain volume variables to build a model that can predict age. So that is our task. So for these 12 volume parameters, they are from several important brain regions, and also we have one parameter measures the total gray matter volume. Okay, so let me just again just try to give you a very brief overview of the machine learning framework. So this framework will be applied to many models we used in these semesters. So the first thing, we need to divide the data into the training and testing subset. And of course, we need to build a model to explain the training data. Then we need to evaluate the training model, the trained model in these training data to see if the model worked well or not. Then we will use this trained model to predict response in the testing data. And in this case, the response is the age. And the model will be based on the brain volume matrix. Then we will evaluate the model performance in the testing data and to see if the performance is consistent in the training and the testing data. So that is the whole framework of the machine learning. Then even with the deep learning we will use in the later course, then we will still follow this framework. So this is very important. I hope you really get insights into this workflow. Then you can apply this workflow to your own data with your own methods. Okay, so to realize this task, then we will just apply the codes that we have used in the previous examples, in the previous workshop. So the first thing is really the same. We will divide the data into the training and testing subsets. And because we no longer use the insurance that we have in the previous example, so in this case, we need to determine the size of the data. So here we use the age variable as the indicator to measure the size of the data. So we use the data.age as the input to measure the length of the data. Then we will use the run sample functions to divide the data into the training and testing at the ratio of the 7:3. Then we will finally obtain the training data and the test data. Then we will use the fit-ln function to do the multiple linear regression. And similarly, in this case, we simply need to define the response variable using age. Okay, so similar to the medical insurance example, then we can once we build the model, then we can use the test data to predict the age as indicated by the yPredict PRED variable. Okay, then we can evaluate the rule mean square errors in the training and testing. So remember that in this RMSE matrix, it just measured the rule mean square difference of the errors between the actual age and the predicted age. So they have the same unit. So here you can interpret that the unit of this number is still the years. It means that in the training model, the error is around the 9.2 years. It means that when you have a brain valence and you derive an age from this model, you will expect that the error is around 9 years. So this is not small. But again, I need to you know that the whole point of this practice is not to build a perfect models. You just try to that you understand the principles of the machine learning, and you can learn how to do this. So maybe you can find a very good models and you have a small errors, but for now we just use the linear regression, and it's reasonable to find that error is not small because the 9 years is still the big errors. But you can find that in the testing data, the error is even larger. It has 12 years of the errors in estimating age based on the brain volumes. Okay, so that is the very simple framework that you can apply the same thing you learn from the workshop and apply to the real world data. Okay. So let's take a look at the results of the multiple linear regression. So in these results, we see that they are not every brain volume, not every brain regions has a significant contributions to the prediction of the brain age. For example, the precentral areas in the regression model is p-value is 0.80. So that means that it is not significant to predict the brain age. And there's in a parahippocampus, and it is very significant because the p-value is smaller than 0.05. Then you will interpret that the parahippocampus is an important region that can predict the brain aging. And again, the parahippocampus is an important region related to the memories. So you can see that even these participants do not have dementia, but during the aging, that these memory-related brain structures have a significant decline in its brain volume. So that is really significant because we can use this regression model to find that which brain region is really contributing to the aging effect. So that is the beauty part of the machine learning, because you can use machine learning to find out answers. And also you can find that the thalamus or maybe amygdala, they have a positive correlations between the age and the brain volumes. And amygdala has been known to be related to like the fear memories or like a stress memory. So it could be reasonable because when we got older and older, we have more any kind of a stressful experience, and that will increase our volumes of the amygdala. And likewise, the thalamus, because the thalamus is the center for any sensory inputs. So just like information centers. So when we got older, then the thalamus should be have more violence because it need to process so many informations. So, but for this model, you can see that only few brain regions has contribution to predicting brain age. And the whole model gives us an R-squared value at 0.75. So that is not bad because with this only few brain regions that we can have a very good model. It has a good fit. Okay, and the model, of course, the whole model is significant. Okay, so that is the regression results from the multiple linear methods. Then, in this workshop, I want to show you something that we can try to improve this model. So comparing to the previous workshop that we just try to examine all predictors in the regression model. But I already showed you that there are some variable selection methods that can help us to simplify the model. And this is very important step because we really don't want so many parameters. Then we want to find just a few subset of the parameters that can explain the response. So for example, in the forward stepwise selection, then in the beginning, we just start with the model with no variables. Then we can find the most significant one, for example, in our data is the parahippocampus. Then we can just put parahippocampus into our model. Then we can evaluate this model, and we can try to find the second one to put into this model. And if we add the second one, the model is better than the previous one, then we will keep these second parameters and these second variables. So we can repeat this procedure until no more variables, or until there's no more significant variables can be added into the model. So this is a forward stepwise selections. And the backward stepwise selection is just the opposite of the forward selections. So in the beginning, we have the full models with all variables. Then and in the next step, we just remove the least significant variables and to evaluate these models. If this model is better than the previous one, then okay, then we will really remove this one, okay, to get rid of this one. Then in the next step, we'll try to get rid of another one and to evaluate if the model is better than the previous one. And then we can repeat this procedure until that no one can be removed. Okay, so that is the very popular variable selection methods. And the true stepwise selection is a combination between the forward and the backward and stepwise selections. So that's what I want to show you, how do we do this in the MATLAB. So in the MATLAB, there's a simple and useful function called a stepwise LM, the stepwise linear model. So for this function, this is very similar to the fit LM. The difference is that in the fit LM, you can also manually add or remove the predictors. But for the stepwise LM, it will automatically do the job for you. So you can see that the argument here is very similar to the fit LM. You can just put the response variable as the age and give the input using the train data variable. Then you will derive a stepwise model here. Then you can also use this stepwise model and to put into the test data to predict the age using the test brain volumes. Then we can also evaluate this stepwise model here. And for this one, you can see that we still have a relatively large the errors in the training model and also in the test model. So remember, in the previous results, when we used all variables, the error in the training model is the 9.2 years, and the error in the testing model is 12 years. And comparable, similarly, that in the stepwise model, we also have the error at the level of the 9.5 years, and also the error at the testing data is the 13 years old. So you can see that the error is a little bit larger when we use stepwise regression. So the point of the stepwise regression is not to help you reduce the error, but to just try to help you to identify those significant parameters that can explain the model. So that is the whole point of the stepwise regression. It cannot reduce the error, but it can help you to reduce the dimensionality of the data. So what that means is that if you look at the stepwise regression results, then you will see that you can say you try to add something into the model. It's the typical steps of the forward selections. The first thing is add the insula, the second step is add the thalamus, the third step is add the parahippocampus, and the final step is add the amygdala. So in this model, they found that the 4 brain regions, including parahippocampus, insula, amygdala, and thalamus, they can all contribute to the brain age predictions, and they have all significant p-values. So, but you will also notice that the R-squared is smaller than the model when you put all parameters inside the model. So in this one, we have the R-squared at the levels 0.70, 0.75, and for this one, for the fewer parameters, the R-squared is smaller, it's 0.1699, it's around 0.70. So it's a little bit smaller than the model used the all parameters. But you can see this model is still better because you only used 4 parameters to achieve this R-squared value. But instead of this, when you use 12 parameters, you only have a little gain in the R-squared. So that is the beauty of the stepwise regression. So for this model, it's very clear that we can only use 4 regions to predict brain age. And that is very useful because maybe we can just focus on these brain regions and to find out what happened in this brain region during the aging. Okay, so the final things maybe in this workshop, maybe we just try to visualize these predictions. So we can compare the actual age and predicted age in the testing data. So we can do this by just type into the plot, test the data.age against the y PRED, and using the O-shaped dot. Then we can also label the horizontal axis is the actual age, and the vertical axis is the predicted age. And then you can see that the model doesn't work quite well because between the age 20 and maybe 45, and the prediction is not doing well. It has a large errors. And also in the older age, there's also large errors. So although the whole things that it is still, if the model is perfect, you should expect to see the straight line, a straight diagonal lines from the 20 to 80. But because our model is not perfect, so you'll see some errors in different age. So that is also an interesting question when we study this data. Okay, so in the final slides, I want to give you an overview of the machine learning method regarding the explainability. So you may be wondering that why we need to learn regression in the first step of the machine learning. Because when we do the regression, you can see that we can find out some useful predictors based on the regression results, and that is the explainability. So for any machine learning methods, they will have different explainability and the ability to achieve the higher accuracy. So in this graph, you can see that the regression has the high explainability, but low accuracy. So for example, in our brain MRI data, we have a very good explainability. We find 4 regions to predict brain age. but the error is not good. The error is around 9 years, is at a low accuracy. So likewise, for other regression methods like lasso regression or logistic regression, they have a good explainability but low accuracy. And also for the other method we will explore in this course, then we will find out that decision tree, they have a better accuracy but a little bit lower explainability. And you can see that for the support vector machine, it can have a better accuracy than the linear regression, but it has a lower explainability. It means that when you do apply these models, you may get good accuracy, accurate predictions, but you don't know why. You cannot, oftentimes then we cannot find out which predictors that is contributing to these predictions. And so you can see that the neural network, which we will learn lots of the neural network in the later half of this course, it has a very high accuracy, but sometimes it's just like a black box. Then we don't know why it derived the answers. So that's what we want to learn in the deep learning, because we want the deep learning to be explainable. So our goal is that if we can make this neural network model to move to this area, so it has a high explainability but also high accuracy. Okay, so I give you this slide as a final slide because I just want to give you an overview that we are here. Then we will try to explore different topics using different methods in the later course. But just keep in mind, there's a trade-off between the accuracy and explainability. Then with the novel techniques, then we can solve these kind of things. Okay, but we need to learn this in the later course. So I hope you enjoy this lecture and workshop. Then and in the next lectures, then we will move to the classifications. So enjoy the course and see you next time. Bye bye.